Welcome to General Chemistry 2 class. This session is on acid-base equilibria and salt equilibria. This lesson is about the effect of common ion on solubility. Let's begin. Objective: describe the common ion effect on the solubility of a precipitate. In a previous lesson on acids and bases, we learned that the common ion effect is a shift in equilibrium position as a result of introducing an ion that is the same with the ion present in the solution. The presence of a common ion affects the solubility behavior of ionic compounds. Consider a saturated solution of lead chloride. If sodium chloride is added, the solution increases in chloride concentration since the chloride ion from sodium is a common ion. Based on Le Chatelier's principle, the equilibrium position shifts to the left towards the information of undesaturated lead chloride. As a result, some of the ions recombine to form the compound. Thus, the solubility of lead chloride lowers in the presence of a common ion. Example number 1. Calculate the molar solubility of silver iodide in 0.0010 molar potassium iodide solution given that Ksp equals 8.52 times 10 raised to the power of negative 17. Solution: potassium iodide is a source of iodide ion, which is the common ion in the problem. For a 0.0010 molar potassium iodide solution, the amount of iodide ion in the solution is initially 0.0010 molar. Now, let us determine the changes in concentrations of silver and iodide ions. Consider the solubility equilibrium for silver iodide. If we let S be the molar solubility of silver iodide, it means that the concentration of silver ion is also S. Since iodide ion has an initial concentration of 0.0010 molar and S is the amount of this ion coming from silver iodide, its equilibrium concentration becomes 0.0010 molar negative S. Write the equation for the Ksp of silver iodide. Substitute the silver iodide value of silver iodide and the obtained expressions for equilibrium concentrations in the equation for silver iodide. Notice that the obtained equation can be simplified by assuming that the value of S is too small compared to 0.0010 molar. To check if our assumption is valid, let us divide 0.0010 by the given silver iodide value. Since the answer is much greater than 1000, our assumption is valid. Solving for S in the simplified equation, we get S equals 8.52 times 10 raised to negative 14 molar. This is smaller compared to 9.23 times 10 raised to the power of negative 9 molar, which is the molar concentration of silver iodide in pure water as calculated from the previous lesson. This proves the effect of a common ion on the solubility of an ionic compound. Example number 2. Calculate the molar solubility of strontium fluoride in 0.020 molar sodium fluoride solution given that its Ksp equals 4.33 times 10 raised to the power of negative 9. Solution: sodium fluoride consists of fluoride ion, which is the common ion. For a 0.020 molar solution of sodium fluoride, the concentration of fluoride ion is also 0.020 molar. Let us determine the changes in concentration of strontium and fluoride ions. Consider Consider the solubility equilibrium from strontium fluoride. Initially, the concentration of fluoride ion is 0.020 molar. If you let S be the molar solubility of strontium fluoride, the concentration of strontium ion in the solution changes from 0 to S, while the concentration of fluoride ion increases by 2S. At equilibrium, the molar concentration of strontium ion is S. For fluoride ion, it is 0.020 molar plus 2S. With the equation for the strontium fluoride, substitute the strontium chloride value and the derived expressions for the equilibrium concentrations of strontium and fluoride ions. To make the resulting equation simpler, let us assure that the value of S is too small compared to 0.020 molar. Dividing 0.020 by the strontium fluoride value gives us a value greater than 1000. With this, we can neglect 2S added to 0.020. Solving for S is a simplified equation. We get S equals 1.1 times 10 raised to the power of negative 5. The example number 3. Calculate the molar solubility of potassium periodate in 0.0500 potassium chloride solution given that its value 3.71 times 10 raised to the power of negative 4. Potassium chloride is a source of potassium ion, which is the common ion to potassium periodate. Since the solution contains 0.0500 molar potassium chloride, the concentration of the potassium ion is also 0.0500 molar. Now, let us determine the changes in the concentrations of potassium and periodate ions. Consider the solubility equilibrium of potassium periodate. The initial concentration of potassium ion is 0.0500 molar. If you let S to be the molar solubility of potassium periodate, the concentration of potassium increases by S, while the concentration of periodate ion increases by S at equilibrium. The concentration of potassium ion is 0.0500 molar plus S. For periodate ion, it is S. Write the equation of the potassium periodate. Substitute the value, the derived expressions for the molar concentrations of potassium and periodate ions. To determine if S added to 0.0500 can be neglected, divide 0.0500 by the value. Since the answer is less than 1000, we cannot neglect the added S. Notice that the equation leads a quadratic equation, which can be solved using the quadratic formula. We obtain two values of S. One is a positive value, while the other one is negative. The second value is not accepted since concentration cannot be negative. Therefore, S equals 0.0066 molar. To summarize, the presence of a common ion reduces the solubility of an ionic compound. This is the bibliography.
Acid-base equilibria and salt equilibria. Part 11. Effect of common ion on solubility. Quiz. Select the correct answer. 1. Which of the following statement is true about the common ion effect? A. It makes the equilibrium position shift towards recombination of ions. B. It plays no role on solubility of an ionic compound. C. It makes the equilibrium position shift towards dissociation of an ionic compound. Or D. It causes increase in solubility of ion compound. Number 2. Which of the following compounds can lower the solubility of FaOH2 in water? A, B, C, or D? Number 3. Which of the following compounds can lower the solubility of LiF in water? A, B, C, or D? Number 4. Which of the following compounds can lower the solubility of FeL with a subscript of 2 in water? A, B, C, or D? Number 5. What is the molar solubility of the compound in 1.0 m NaCl? A, B, C, or D? Number 6. What is the molar solubility of the compound in 0.80 m PbNO3 2? A, B, C, or D? Number 7. What is the molar solubility of the compound in 2.25 compound in 0.25 m BeCl2? A, for B, C, or D? 8. What is the molar solubility of the compound in 0.10 m Na2CrO4? A, B, C, or D? Number 9. What is the molar solubility of the compound in 0.50 m CaCl2? A, B, C, or D? And number 10. What is the molar solubility of the compound in 1.0 times 10 raised to negative 4 m NaIO3? A, B, C, or D?